3.6, the graphing of rational functions. And we'll start with the definition. A rational function is simply two polynomials divided by each other, the quotient or the ratio of two polynomials. A polynomial in the numerator, a polynomial in the denominator. And what we're going to find out is there are going to be some special circumstances that we have to look at in terms of graphing these rational functions. The first is going to start with the concept of domain restrictions. Whenever you have a fraction, remember, you can never divide by 0. And so this rational function is going to be legitimate across all real numbers as long as the denominator is not set equal to 0. So in this case, our function x plus 1 over x squared minus 3x minus 4, it's a legitimate rational function. Its domain is going to be all real numbers with the exception of those values where x squared minus 3x minus 4 is equal to 0. Or if we factor x minus 4, x plus 1 can't be equal to 0. And so we're going to find out we have, I call them trouble values. Values at which this rational function cannot exist are going to be true at x equals 4 and at x equals negative 1. Those are the values that are of x that would set the denominator equal to 0. So just make note, values of x that are root zeros of the denominator will make the rational function undefined and therefore will restrict the domain of the rational function. And so if we wrote the domain of this particular function, we could say, well, our domain is all real numbers. And then right after that, I could list our exceptions. X not equal to, in this case, we had what? Negative 1 and 4. And this same thing we could put in, just kind of circle it. We could put in our longer handwriting, unfortunately, but still legitimate, interval notation as negative infinity to negative 1 with parentheses, union, everything between 1 and 4, and then close out with 4 to infinity. That's the same thing. Obviously a little bit longer to write in interval notation, but I want you to be familiar with using it and understanding these two different things are the same concept, just presented in two different types of notation. So if you recall what you did in Algebra 2 and what we've already talked about when we did this lecture before, remember this is kind of a recap. Each restricted value of x, in this case the values of x equal negative 1 and 4, are going to represent something in our graph. It could be a vertical asymptote, a dashed vertical line that shows spots where the function does not exist, and that's going to take place whenever that factor number, if x equals b is a root, x minus b is a factor. If the factor x minus b shows up both in top and bottom, numerator and denominator, when we have something like that, they cancel each other out, and we will have something called a whole. But if we can only see that factor x minus b in the denominator, we're going to have a vertical asymptote. So a whole is just simply, just like that, an open dot on our graph. A vertical asymptote will be drawn as a dotted vertical line. Just to reiterate, a vertical asymptote occurs at x equals b in our rational function when x minus b is a factor of the denominator only. A whole occurs at the x-coordinate, we'll say at the x-coordinate of b, when x minus b is a factor of both the numerator and denominator. So let's look at a few examples. And we'll go ahead and start with this first function that we see here, which is f of x equals 2x squared plus 3x minus 2 over x squared minus x minus 6. I'm going to go ahead and factor both numerator and denominator. X minus 3, x minus 2 up top. And when we do a little bit of decomposition over here, I'll let you work on this on your own. 2x minus 1, x plus 2 is what we will see here. So, where are our two trouble values? Well, we're going to have a trouble spot at x equals 3. We're going to have a trouble spot, x minus 3, x plus 2. My fault here. Just as I was working that, so go ahead and please make your change. Sorry about that. Here we have x equal negative 2. These are our two domain restriction values. Every other real number is great, but x equals 3, x equals negative 2, set the denominator equal to 0. When we look at x minus 3, or this root at x equals 3, what do we notice? X minus 3 only appears in the denominator. This is going to be a vertical asymptote. And here's our calculator graph. You can't quite see it because the calculator can't show vertical asymptotes, but there's a break in our graph. And at the line x equals 3, it represents a wall between two pieces of our function. When we have x equal negative 2, we have that same factor, x plus 2 in both numerator and denominator. This is going to represent where the x coordinate is equal to negative 2, we'll actually have a hole. And just for grins, let's go ahead and do something very quickly. As long as x equals not equal to negative 2, well, what happens? We can go ahead and let these factors cancel each other out. And so generally this function would look like 2x minus 1 over x minus 3. And if we plug in a value of negative 2, we'll find out 2x minus 1, 2 times negative 2 minus 1, negative 5 over negative 2 minus 3, negative 5. Our value of the function, if they had not caused a 0 down here at the denominator, we actually would have had negative 5 over negative 5 or positive 1 as our f of x value when x is right around, not exactly equal to, because remember, they cancel each other out. But the bottom line is, I do know that I'm going to have a hole at an x coordinate of negative 2. And if I actually had to place this on the graph, just something to kind of think your way through, that would live at the point negative 2, 1. That's where the actual hole would live in this graph. For the moment, your key focus is just knowing the x-coordinate of x equals negative 2 is going to be the location, the x-coordinate location, as to where that hole is. In terms of where the exact y-coordinate that goes along with it, remember, a hole is a point, just a little bit more elimination work you have to do. So let's keep working. Go on to our next page, which will have a few more problems of the same ilk. And all you're really asked to do is identify your vertical asymptotes. X plus 5 over x squared plus 3x minus 4. Numerator, x plus 5, leave alone. Denominator factors into x minus 4, x plus 1. What are you going to find? Well, at x equals 4 and at x equals negative 1, those are your two trouble spots. If I wanted to write the domain, I'd be from negative infinity to negative 1, union, negative 1 to 4, union, 4 to infinity. And in both cases, x minus 4 only lives in the denominator. X plus 1 only lives in the denominator. This graph would have two vertical asymptotes, one at x equals 4, another at x equals negative 1. And we look over here, by the way, what will we see? Hey, it's already factored. X equal negative 3, x equal negative 2. At x equal negative 3, there's the associated factor, x plus 3. Doesn't have a partner above. Vertical asymptote. X plus 2. Absolutely. I'm going to have a hole at an x coordinate of negative 2. And by the way, again, if I wanted to find the y coordinate of the hole so I could actually place the hole on my graph, well, what would I evaluate? I'd look at x minus 3 over x plus 3 with a value of x equal negative 2. What I've done here is I've just done some simple algebra. Everywhere else, the x plus 2 over x plus 2 cancel each other out as long as x is equal to negative 2, where I'd blow up this fraction. So if I plug in negative 2 minus 3, negative 5, negative 2 plus 3, positive 1, the actual location of the hole, negative 5 over 1 is negative 5. The actual location of the hole would be at 2, negative 5. So again, focus on just knowing that you do have a hole here. You wouldn't be drawing a vertical asymptote. But again, with just some simple algebra and some substitution, we could actually find the true location, the xy coordinate of that hole. So there's some work with vertical asymptotes and holes. Let's go ahead and handle our second thing. How to identify the horizontal asymptote of a rational function. Remember, an asymptote is what? A line that you approach but do not touch. It can be horizontal or vertical, as we've already seen. Horizontal asymptotes, to figure this out, you need to compare the degree of your numerator against the degree of your denominator in your rational function. If the denominator has a higher degree, you're going to have, just as you see in this example, first case, degree 1 over degree 2 polynomial, you're going to have end behavior horizontal asymptote at y equals 0. By the way, a horizontal asymptote represents end behavior. What happens way over here and way over there as x approaches negative infinity, as x approaches positive infinity. That's where horizontal asymptotes live. I like to describe them again. Horizontal asymptotes don't live in the middle, they live at the ends. Again, if, I call it a degree battle, if your degree is higher in the denominator, you're going to have a horizontal asymptote on your graph at y equals 0. If the numerator has a higher degree, you're not going to have a horizontal asymptote. The function keeps getting bigger and bigger, either more and more positive or more and more negative. It does not have a boundary to it. And finally, if the degrees are the same, if there's a tie, the numerator and the denominator are the same degree, go and look at the coefficient, the leading coefficient that goes with the high degree term, and then take the ratio of them. And that's what you see down here. You see 2x squared plus 3x minus 2, x squared minus x minus 6. Both are second degree polynomials. To figure out your horizontal asymptote, you look at the high degree coefficient up here, which is a 2. And the high degree, what coefficient goes along with the x squared term in both these? 2 over 1. You're going to have a horizontal asymptote at y equals 2. And if you look at the calculator graph, you can see that happening. Again, it's end behavior. There's where my horizontal asymptotes lie. So very simple process of figuring out horizontal asymptotes. Be comfortable with that. Our final step is to cover graphing rational functions, showing a lot of key pieces. And so we'll go ahead and start to do that. I'm going to have just a little bit of tightness in terms of how much space I have here to work. You will use your calculator to assist you in these problems as well. So as I get ready to talk about this, I'm going to go ahead and build my first function, which is x divided by x squared minus x minus 2. And so I'll have that built into my calculator, and I can graph that, and we'll come back to the graph in a moment. In the interim, what else do I know about this function? Well, go ahead and factor numerator and denominator. X squared minus x minus 2 becomes x minus 2, x plus 2. What am I going to have? I'm going to have a domain of all real numbers. My trouble values are x cannot be equal to 2 or negative 1. Another way to write it, negative infinity, negative 1, union, negative 1, 2, union 2 to infinity. Vertical asymptotes or holes? Well, let's look. What do I notice? X minus 2, x plus 1, they don't have partners in the numerator. So at x equals 2, I have a vertical asymptote. At x equals negative 1, I have a vertical asymptote. I can go to my graph and I can put them in. Here comes my vertical asymptote at x equals 2. Here it is at x equals negative 1. Now there's more I can do. I can identify my horizontal asymptote by doing the degree comparison. Numerator degree 1, denominator degree 2. Denominator wins. Y equals 0 becomes my horizontal asymptote. So I'll go ahead and dot my far right and my far left. I could dot the middle if I'm so inclined as well. No reason not to do that. But just for the purposes of what we're showing, I'll just go ahead and do it on the outside. By the way, the horizontal asymptote perfectly defines your end behavior. As x approaches negative infinity, g of x approaches 0. That's what this horizontal asymptote is showing. And the same thing is true as x approaches positive infinity. G of x approaches 0. Bottom line, if you know your horizontal asymptote, you know your end behavior in both directions. There's a couple more things that I can do to make the job a little bit easier. That's to identify x and y intercepts. Well, how do I identify the y-intercept? Set x equal to 0. In this case, when I set x equal to 0, I'm going to have 0 over negative 2. And so the y-intercept lives at 0, 0. I'm going to go ahead and dot it. To find x-intercepts, well, what do you require? You require that your numerator be equal to 0. And it turns out my x-intercept lives at, and shouldn't be too much of a surprise, at the exact same point. So I have all the easy work done. I have labeled asymptotes. I found kind of the low-hanging fruit, x-intercept, y-intercept. In this particular problem, they happen to be the same thing. And so my last piece of work is to do nothing more than to go to my graph. And here we are. Here are the general shapes. I can see I have 3 sections. I have an interesting middle section. Let me go to a zoom standard real quick on my window here. I had made my axes pretty big at the moment. Here we're going to get a better kind of bigger picture look at this. And so what can I do? I'm going to go ahead and build that graph. On my first side, I'm going to be doing what? I'm going to be approaching 0 as I move towards negative infinity. Don't forget to get arrows in both directions. I'm going to handle my other section, which is over here and runs towards x equals 0. Excuse me, y equals 0. And finally, my inside piece looks a little bit like a kind of a y equals x cubed graph, kind of one of those little shapes, but it's very, very steep. Not quite symmetrical, but it'll run something like this. So my graph is built, and then the last piece is that I see here from a question standpoint is to just do the range. Well, in this case, if I didn't happen to have this middle section, I might have kind of a split range. But the nice thing about this little middle section, the middle tier, so to speak, of this graph between these two vertical asymptotes, it happens to run from negative infinity to positive infinity. My range is nothing more in this example than all real numbers. Okay, so very quickly, I'm going to go ahead and get ready to set up my next example. I'll give you a couple seconds to just look at how I factored this and agree that both forms that I have here are good. In the interim, I'm going to go ahead and go to my calculator. And I'm going to go ahead and build into my y1 this new graph after I clear out the old. I had 2x squared minus 4x plus 2 divided by x squared minus 9. Notice I like to use parentheses for my numerator and denominator. I'll go ahead and hit my graph button, but let's go ahead and do some of the manual work now on this problem. 2x squared minus 4x plus 2, I could take out a 2 and do a lot of factoring, or I could just use decomposition. Trust in tech that 2x minus 1 is legitimate. X squared minus 9, difference of 2 squares. I hope you see that pattern. X minus 3, x plus 3. And by the way, 2x minus 2, if I take a 2 out, x minus 1. So I have 2x minus 1, x minus 1, over x minus 3, x plus 3. Trouble values. X equals 3, x equal negative 3. Neither of those factors cancel each other out. I'm going to have vertical asymptotes at x equals negative 3 and positive 3. By the way, for a domain, all real numbers, x not equal to negative 3, comma 3. Interval notation, negative infinity, negative 3, union, negative 3 to 3, union 3 to infinity. Let's do one more thing, then I'm going to go ahead and move down to the graph and start splashing some things out. Horizontal asymptote, 2x squared minus 4x plus 2, x squared minus 9. Degree 2 in both cases. Tie, I need to look at the coefficients. the x squared coefficient specifically. 2x squared, x squared, 2 over 1. My horizontal asymptote occurs at y equals 2 over 1, or y equals 2. So, here I go. Vertical asymptotes, -3. +3. Great. Horizontal asymptote, y equals 2. I'll go ahead and dot again. Now, there might be one interesting thing that you kind of noticed. We'll talk about this just very quickly. I can go through a horizontal asymptote. Just kind of make note of that. One thing to keep in mind, you can never cross a vertical asymptote. It's possible that the y value of your horizontal asymptote, yes, is something that you could go through. And behavior. Well, as x approaches -infinity, f of x approaches 2. And the same thing as x approaches +infinity. Important point, your horizontal asymptote defines the end behavior in both directions. X-intercepts, do I have a point this time? Well, set the numerator equal to 0 to get x-intercepts. How do I make 2 times x minus 1 times x minus 1 equal to 0? Can't ever make a 2 equal to 0. Excuse me, just move here. But as soon as x equals 1, I definitely will have a value of 0 in my numerator. So the point 1, 0 is a legitimate point that I want to go ahead and dot on this graph, which I just did. If I want to find the y-intercept, what do? Set x equal to 0. 2x squared becomes 0. 4x becomes 0. Plus 2 over what? 0 minus 9. Plus 2 over -9. The y-intercept lives at 0 and -2/9. And so I can go ahead and dot that. Won't be able to do it perfectly, but there's my y-intercept, that little red dot. I can go to my calculator and get a view of the graph. And again, it's a 3-parter, so to speak. And what am I going to be doing? Well, I'm going to be writing off to my end behavior at y equals +2. I'm going to have that same thing happen over here with something that's just a little bit interesting. Can't quite see on your calculator. And if we had Desmos or something where we could really view this in, you could see a better scale of this. But one thing, our middle section, whoops, let me bring it back up. I turn my calculator off. Looks like a somewhat lopsided parabola. I'm going to go ahead and touch that up in the middle here. Make sure I hit my 2 points. And down I go. So I didn't do quite as good a job in my drawing there. You can kind of see how the parabola is a little bit more lopsided than what I'm kind of showing in my drawing or whatever. It doesn't quite show to scale compared to what the calculator is, but I have a pretty good representation here. And what we see in this example, we're not going to worry about this piece, but I just want you to see it just for the purposes of accuracy. Notice the graph actually went under part of the horizontal asymptote. That is okay. The horizontal asymptote, remember, really only lives at the far ends, not in the middle. So we've talked before, you can't go through a vertical asymptote, but you can kind of see your graph doing some interesting things, so to speak, about a horizontal asymptote. This also, by the way, would be an example of where we're going to have a split range. Not like in our first problem when we had everything covered, thanks to this nice little middle section. Well, here our middle section covers some stuff, but what? There's definitely a gap that we would see here. So in this case, our range is going to be -infinity to 0. And by the way, I'd put a bracket on the 0 because we actually hit that value. And then we'd see if we worked with the calculator here. my y value actually dips just a little bit below. And again, this is something you'd have to see on your calculator. It's not something that you would intuitively see or whatever. But we just wanted to make note here that we would be seeing a split range. And what I'm going to say, just in terms of looking at this, that value is about 1.7, the lowest value that I would see. This piece kind of always stays above y equals 2. This piece dips a little bit under. Again, you'd have to find that in your calculator. But for the moment, the key thing that I want you to focus on are the following pieces. Range is a valuable after sight, but it's everything up top that I really want you to focus on. So there you go, 3.6 in maybe not a nutshell, but maybe a few nutshells. All the pieces that you need to understand this unit and be ready to work with it.